Quantum physics. The term quantum refers to the smallest discrete unit of any physical property in quantum mechanics, the branch of physics that deals with the behavior of matter and energy at a very small scale, such as atoms and subatomic particles. The Latin word quantus, meaning how much, and is used to describe a fundamental packet of invisible quantity of energy, matter, physical property in the realm of quantum mechanics. Quantum energy. In the context of quantum mechanics, a quantum refers to the smallest possible unit of energy that can be emitted or absorbed by an atom or particle. Max Planck proposed that energy is quantized, meaning it is emitted in discrete units rather than a continuous flow. For example, in the case of electromagnetic radiation, light comes in discrete packets called photons. Each photon carries a quantum of energy that is proportional to the frequency of radiation. In the Bohr model of atom (1913), Niels Bohr proposed that electrons orbit in the nucleus in discrete energy levels or shells. When electrons move between these levels, they do so in a quantum leap, absorbing or emitting a specific amount of energy in the form of light. This idea marked a shift from classical physics, which viewed energy as continuous. Quantum mechanics describe how particles like electron, proton, and photons interact and how they behave in various states, often involving phenomena like superposition, entanglement, and wave-particle duality. At this microscopic level, the traditional law of classical physics do not apply. Instead, quantum mechanics govern how particles move and interact in ways that can be probabilistic and uncertain. One of many discoveries that came with quantum mechanics is wave-particle duality. Quantum mechanics revealed that particles such as electrons and photons can exhibit both wave-like and particle-like behavior. This phenomena is known as wave-particle duality. For example, electrons can behave like waves, showing interface patterns as seen in double-slit experiment, but also exhibit particle-like properties when interacting with matter. Light, which was once thought to be only a wave, also behave as discrete particle called photons. This dual nature is central to the understanding of quantum phenomena. Another interesting discovery was superposition. In quantum mechanics, particles do not have definite position or multiple states until they are measured. Instead, they exist in superposition of all possible states. This means that quantum particle, like electron, can be in multiple states at the same time. For example, an electron can simultaneously be in different energy levels or locations. The superposition of states is described by a wave function. This contains all the possible outcomes of measurements. Once a measurement is made, the system collapses into the one of the possible states. Quantum mechanics introduced the idea of quantization, where certain physical properties such as energy, angular momentum, or charge can only take on a discrete value rather than any value within a continuous range. For example, the energy levels of electrons in an atom are quantized. They can only occupy a specific fixed energy level and not values in between. Uncertainty principle. One of the most famous and profound concepts in quantum mechanics is Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927. The principle states that it is impossible to simultaneously know both the exact position and momentum of a particle with absolute certainty. The more precisely one of these quantities is known, the less precisely the other can be known. This uncertainty is not due to limitations in measurements, but it is inherent to the nature of the quantum system. Quantum entanglement is one of the most intriguing and mind-bending phenomena in quantum mechanics. It refers to a special kind of relationship between particles where the state of one particle is directly related to the state of another, regardless of the distance between them. When particles become entangled, their properties become interdependent, and a change in a state of one particle will instantaneously affect the state of another, even if they are separated by vast distances. This phenomenon defies classical concept of locality, the idea that objects are only directly influenced by their immediate surroundings and causality, which underpins much of classical physics. The term quantum entanglement was coined by physicist Erwin Schrödinger in 1935, who called it a spooky action at a distance, a phrase that has become iconic in describing the non-local nature of entanglement. When two particles such as photons, electrons, atoms become entangled, they form a single quantum system. The properties of a particle such as spin, polarization, or position are correlated in such a way that measuring one of them will instantaneously provide information about the other, no matter how far apart they are. For example, if two entangled particles are created in such a way that their spin are opposite, when you measure the spin of one particle, you will know the spin of the other, even if the particles are light years apart. The most striking feature of quantum entanglement is non-locality, the idea that entangled particles can influence each other instantaneously, even across vast distances. This seems to violate Einstein's theories of relativity, which asserts that information cannot travel faster than light communication, and no information is transmitted in the traditional sense. The spooky aspect comes from the fact that measurement outcomes are correlated without any known signal traveling between the particles. Before measurement, entangled particles exist in a superposition of multiple states simultaneously. This means that, for instance, an electron in an entangled pair that may have a spin that is both up and down until one of them is measured. Once a measurement is made on one particle, the superposition collapses and the state of the second particle is instantaneously determined, even if light years away. The measurement is probabilistic, meaning that you cannot predict the exact state of each particle before measuring. The only thing you can know is that two particles will have related outcomes. In 1964, physicist John Bell formulated a theorem that shows how quantum mechanics predictions for entangled particles contradict those of classical physics. According to Bell's theorem, if the world were governed by classical theories, the correlation between entangled particles would follow certain limits. However, experiments have shown that quantum mechanics predictions hold true, demonstrating that nature behaves in a fundamentally non-local way. Aspects Experiment 1982 In a landmark experiment conducted by Alain Aspect and his colleagues, the violation of Bell's inequalities was confirmed, providing experimental evidence for quantum entanglement. The experiment showed that the particle properties were indeed correlated in a way that couldn't be explained by classical physics. Entanglement swapping is a phenomenon where two particles that have never interacted can become entangled through the entanglement of their partners. This can be experimentally demonstrated and have application in quantum communication. Quantum teleportation is a process that uses entanglement to transfer quantum information such as quantum state of a particle from one place to another without physically moving the particle itself. This does not violate the non-faster-than-light rule, because the actual transmission of quantum state still requires classical communication, but it allows for the transfer of quantum information over long distances, enabling potential future technologies like quantum networks. Quantum tunneling is a phenomenon in which particles can pass through a potential barrier such as an energy wall that it would not be able to do in classical physics. This happens because of wave-like nature of particles. In quantum mechanics, the particle's wave function has non-zero probability of leaking through the barrier even if the particle does not have enough energy to overcome it. This principle is important in many physical processes, such as nuclear fission in stars. Quantum field theory is a framework of combining quantum mechanics with the special relativity. It treats particles as an excited state of underlying fields, rather than discrete particles. One of the most famous quantum field theories is quantum electrodynamics (QED), which describes the interaction of light and matter. QFD led the development of Standard Model of Particle Physics, which explains how fundamental particles interact through the electromagnetic weak-strong forces. Applications include quantum computing, quantum cryptography, semiconductors and transistors, MRI and medical imaging, and lasers. Thank you for listening to this podcast on quantum physics. Until next time, curiosity, adventure through scientific fields.